going to the wind tunnel to tour the testing by Electra. So this is actually quite a unique opportunity because I myself, before I get to MIT as a professor, I've never seen wind tunnel testing of something that's actually supposed to fly. So I've seen like class projects, like research projects, but like this is something, and you're going to see like basically something. So Electra has a technology demonstrator flying, but like what they are testing right now is not the demonstrator, but like the actual product they are going to build, like a much bigger airplane than the demonstrator. So it'll be interesting for you to see and go ask questions. So I asked our TA to send you email ASAP on like which session we'd like you to be in, but like we're going to meet in the Unified Lounge and just walk there together. All right, question? I just realized you didn't get a confirmation. I asked our TA to just send you email ASAP. Hopefully before the class ends, you should get the email. All right. Okay. So today is the first class on compressible flow. So in compressible flow, I think as you notice, the pace of the lecture seems to be getting faster and faster, and that's actually what we have to do in compressible flows. Because we actually need to get through compressible flows for you to be able to do your project. The project is going to be not on low subsonic flows, but on transonic flows. So let's get started. Aerodynamics changes at higher Mach number. So this is basically the plot of a CFD on here. It's already transonic, but like it's already compressible. What I should say. But if you look at the pressure distribution, it is qualitatively similar to what we expect for a subsonic flow. Right. So on top of the airfoil, you have blue, which is a low pressure. On the leading edge, you have red, which is high pressure, and the low pressure recovers to something yellow, moderate pressure. On the suction side, on the pressure side, right, you have this is actually at a slightly negative angle of attack, so you still have a leading edge suction, but like on the lower side. So this is a highly cambered airfoil, as you can see, right? And then the pressure becomes high and higher and higher. So essentially, what you see is on the suction side, you have a suction peak around here and recovers. On the pressure side, you have almost a favorable pressure gradient. No, actually, you have a suction peak and you have adverse pressure gradient also along the way. So it's essentially the same as a cambered airfoil at a slightly negative angle of attack, predicted by thin airfoil theory. Now let's actually look at this CL versus Mach number plot. And this is the peak, right? As you can see, as I further increase the Mach number, the CL is going to plummet to something negative. So this is at the same angle of attack before it recovers to a slightly negative CL. So what is actually happening? So let's actually look at the next few plots. Okay, so here is the pressure at the next Mach number, slightly higher. So you don't see any qualitative change yet, but in quantitative there is a little bit change. So what has happened between this plot and this plot on the upper side? So this is lower Mach number, higher Mach number, lower, higher, lower, higher, lower, higher, lower, higher. Notice anything? Again, lower, higher, lower, higher. Nothing qualitatively changed, but there is a quantitative difference. So, okay, let me go through. Sorry? Yeah, the blue region seems to expand, right? So I'm actually going to step through three Mach numbers: the lowest, medium, higher. Low, high, high. Right? So the blue region expands. The part of the low pressure region now starts to expand further downstream. Okay? So we're going to see why that is the case. also look at the lower side, it's going to be even more dramatic. So let me just get the 3 plots to the same location. So lowest Mach number, higher Mach number, higher Mach number. Okay, lowest, higher. So basically the blue region, right, of low pressure just expands toward the trailing edge. And the expansion is more obvious on the lower side. And this is the expansion, the increased expansion on the lower side is what drives the lift coefficient to drop, right? Because no longer only the suction side has a suction. The pressure side now also has a significantly expanded region of suction going on. So this is where the lift coefficient is already negative. All right. Okay, so going further, you can see on the lower side, on the so-called pressure side, the low pressure region expands almost to the whole wing, while on the supposedly suction side, it expands, but still there is a region on the trailing edge that's actually a high pressure, right? Where this is basically super negative lift coefficient. Okay, and now somebody tell me, why does the lift coefficient recover to something slightly negative? No, it's because the upper side also expands, right? The low pressure region on the upper side also expands all the way to the trailing edge, right? So on the previous figure, the low pressure region on the lower side already expands all the way to the trailing edge, but on the upper side there is still a sliver of positive pressure, and at this point, beyond, like, everything is negative already, right? So basically, what is going on? So we're going to see a little bit later that the expansion of this blue region is actually an expansion of a supersonic region, right, in the flow field. So although if you look at here, even if you look at the lowest Mach number we have looked at, this one, there is already appearance of supersonic regions actually just before the shock wave. I mean, here you can actually, the region between the blue and the downstream green is actually a shock wave. So before the shock wave, there is already supersonic regions appearing also here. And so we're going to see, like, why the flow becomes supersonic, even though the airplane still flies at Mach 0.75, right? So the airplane flies 3/4 of speed of sound, but locally there is flow actually over speed of sound. And as you fly faster and faster, the region of supersonic flow expands both on the upper and lower side, and expands further on the lower side. And eventually that's what's causing the lift coefficient to decrease rapidly. And along with the lift coefficient, should also, if you plot the drag coefficient also increases very rapidly, okay? And the moment coefficient also changes pretty dramatically over the process. So there is a huge impact of supersonic flows when the airplanes fly in the transonic region. And today is the first lecture we are going to start looking into why all of this is happening. Okay, so before we look into the macroscopic effect of compressible flow, so we actually have to start from the microscopics. So you did the thermal unified, right? But like from my experience, everybody at this point already forgot pretty much all of it. So let me basically start from reminding you about the basics. So the thermodynamics of air, so we are going to be strictly talking about air here. And we're strictly going to consider air as an ideal gas. So Professor Harris is going to give some guest lectures on high supersonics and hypersonics. There are situations where you cannot consider air as a ideal gas, but that's at very, very high Mach numbers. So for I would say for most of the, before you get to like Mach 7, 8, we can pretty much consider air as an ideal gas. Okay, so for ideal gas, if you take a bunch of air, the bunch of air is purely defined exactly by two things. What are the two things? pressure, temperature, right? Or I mean, you can actually give me two arbitrary things, and I can define air. But from a microscopic point of view, the bunch of air is defined by, okay, what is how much energy is there in the molecular motion? Okay, so this is pretty much temperature. And also, how much space is occupied by the air, right? That's pretty much volume or density. So, or you can give me pressure or temperature, or temperature and the density. So basically, two numbers, I'm going to uniquely determine what the air is doing. Okay, so now given that knowledge, and that's and the knowledge the pressure is equal to rho RT. So R is basically a quantity that depends on the molecular weight of air. So basically, let's consider R as a constant. And the pressure is proportional to density, is proportional to temperature. So that's the only thing you have to actually just remember about thermodynamics. Okay, and we can actually derive everything else. Okay. So here I'm going to show you one derivation of a quantity that's going to be very useful. But in the process, I think I want to introduce really a way of thinking that's actually immensely useful. Not just in compressible flow, but in pretty much all engineering disciplines. So have you heard of the word the fractional sensitivity? What is that? Exactly. If you change something by a fraction, how does something else change? So the easiest fractional sensitivity is something that's linear or proportional. Okay. So for example, in my previous formula, T equal to rho RT, right? So if R and T, so R is fixed. If temperature is fixed, then T is proportional to rho. Which means if rho increases by 1%, how does T increase? 1%, right? Okay. On the other hand, if rho is fixed, T increases by 1%, P also increases by 1%. If both rho and T increase by 1%, P increases by about . So if rho increases by 1%, T also increases by 1%, which means rho becomes 1.01, T becomes 1.01, P becomes about 1.02, right? It's actually 1.0201. But if you look at a small fractional change, it actually changes product into summation. That's pretty much the power of taking log, right? So a fractional change basically is defined as a delta rho over rho, where the delta is very small. So if you take log on everything, you're going to find out the delta P over P is going to be equal to delta rho over rho plus delta R over R, which is 0 because R is a constant, plus delta T over T, right? So basically, this is essentially taking log on both sides and taking a small change. And the small change of the logarithm is dp over p, right? d log p is dp over p. That's the derivative of logarithm. That's why, like, when you look at fractional sensitivity, you change product into summation. That is why when rho increases by 1%, T doesn't change. This increases by 1%. If rho and T both increase by 1%, this increases by about 2%, right? Whenever you're talking about small change relative to the base value, fractional sensitivity is very useful. Okay. Another thing is, for example, for example, lift is equal to a half rho v squared times CL, right? So suppose CL is fixed. You increase velocity by a small fraction, by 1%. How much does lift increase? No, velocity increases by about 1%. How much does lift increase? 0.01%. Yeah, right. So if V becomes 1.01, L becomes about 1.02. So if V increases by 1%, L increases by 2%. That's the power of the square, right? Square is basically V times V, and similar to here, right? Basically, if you take a delta L over L, is going to be equal to 2 times delta V over V. Suppose rho and the CL are fixed. Agreed? All right. Another thing I think I want to point out is the reciprocal, right? So for example, if I rewrite the formula here, if I rewrite this formula here as, for example, rho is equal to P over RT, right? And I'm asking, okay, if temperature increases by 1% and pressure is fixed, how would my rho change? It decreases by 1%, exactly. So a division becomes a minus, right? Okay, so in the fractional sensitivity sense. So again, let me just summarize. A product becomes summation, a power becomes product, and the division becomes subtraction. So basically that kind of helps a lot of analysis. All right. So for example, like if I have a power due to drag is equal to half rho V cubed times CD, right? That's basically the drag times speed, right? So if velocity increases by 1%, how much does the power due to drag change? 3%, exactly. Okay, so now you know all of it. So for example, here I'm going to give a few questions. So because I want to go fast here, I'm going to work out these solutions for you, but I would like you to treat it as if you have to come over and do it, right? Because the quiz is going to be the week after next week, right? I mean, like these are the similar stuff that will be appearing on the quizzes. Okay, so now we know P equal to rho RT, right? For a fixed mass of air, what is the fractional sensitivity of the volume to its density? Can somebody answer me to that? Yes, the fractional sensitivity is -1, right? Because for fixed mass of air, we know m is equal to the rho times v, right? So volume to density means like the volume, for example, right? Rho is equal to m over v. So a delta rho over rho is going to be, well, delta m over m, which is 0. We know m is fixed, minus delta v over v, right? Which means, okay, for a fixed mass, if volume increases by 1%, the density is going to decrease by 1% about, right? Okay, make sense? All right. So second question, at a fixed temperature, what is the fractional sensitivity of the volume to its pressure? Yes, again -1. Why is that the case? I think most people haven't got the -1 yet. Can you help explain?
I mean, rho is m divided by v, so we take the beta to understand the gate PV is equal like constant.
Right. Okay, so for a fixed temperature, this is fixed, right? So according to this formula, we have delta P over P is equal to delta rho over rho, right? But we have already derived that delta rho over rho is minus of delta V over V, so this is also equal to minus delta V over V. Which means if volume increases by 1%, pressure would decrease by 1%, given constant mass and the constant temperature, right? Okay. So what does this mean, actually? So this is basically gives a relation in the PV diagram, right? So if I do a diagram, if the horizontal axis is P, the pressure, vertical axis is volume, of a particular mass of gas, what would the constant temperature line look like given this formula? The reason I'm drawing a log plot here is because the fractional sensitivity, right, delta P over P, is actually equal to a delta log P. Delta V over V is actually equal to delta of log V. I mean, these are basically the amount of change in the log-log plot. This formula basically saying that the amount of change for a constant temperature, constant mass, the amount of change in P in the log diagram, basically the horizontal axis, is going to be exactly negative of the amount of change in the V, in the log scale. So what would the line look like? Exactly, it's a negative slope of slope exactly equal to -1. Okay. Yes?
By saying the graph, I mean like the delta P and delta V graph? Or?
This graph is a constant temperature line. So with a constant temperature, if I expand the volume by something, right, I'm going upward in the V axis. So by this relation, I have to go leftward in the P axis. And the amount of leftward I go is exactly equal to the amount of upward I go here, which means I have to follow this 45-degree line. If I have a different temperature or lower temperature, I would have a different 45-degree line. But every temperature is going to be a 45-degree line, period. All right, in the PV plot, if I have both axes in log scale. All right, make sense? Okay, so now let's derive something actually useful. All right. So basically, this is the answer to the previous question, right? The fractional sensitivity of volume to density is -1, volume to pressure is -1. At constant temperature, we have a slope -1 come to us. All right. Now actually consider a physical process. Actually, two physical processes. One physical process is add the infinitesimal heat at a constant volume. Okay, so if I draw a PV diagram, what does that mean? So if this is P, if this is V, and imagine I'm drawing it in the log-log diagram. But because it's infinitesimal, right? I zoom in the log diagram, and if you ever zoomed in into a log diagram, you know, like when at the zoomed in scale, a log plot looks pretty much like a linear plot. Right, the difference in a zoomed out view, you have the changes are very nonlinear, but once you zoom in, it looks pretty uniform. All right. Okay. Anyway, so process 1 is I add heat at a constant volume. What does that process look like in the PV diagram? If I draw an arrow, right, add heat at constant volume, what would that arrow look like? This way? Yes. Why?
Volume should stay constant.
Volume stays constant, so it has to be horizontal, right? And when I add heat, how does the pressure change? Increases, right? Okay. Yeah, increases. So process 1 would go like this. So this is process 1. Now process 2 is I add the same amount of heat at constant pressure, followed by isentropic compression to the original volume. All right. So first of all, let's pause a little bit and think about why the two processes should get to exactly the same final state. I added the same amount of heat, right? And isentropic compression means, right? Right, so I added the same amount of heat right? And then at the final, basically the amount of energy I give to the system of the overall process is actually exactly the same, right? So basically the molecules by the end of the two processes would be moving on average at exactly the same speed. And at the end of the two processes, I'm also occupying exactly the same volume. So these two processes should get me to exactly the same state. But now let's look at the process 2. First of all, the first part of process 2 is green, and let me just use green to draw the first part. And what would the first part do? Go upward, exactly. Go upward. And then the blue process is the isentropic expansion. It is going to go exactly back to the same state, right? So this is the green is 2A and the blue is 2B. So let's figure out what is the slope of the blue line. What is the slope of 2B? Given that, okay, the heat capacitance ratio under constant pressure is equal to 1.4. I mean, that's the heat capacitance ratio of air, right? And that's another thing you probably have to remember for air, which most of the air molecules has two atoms. And the 1.4 is actually for gases that has two atoms. So air actually has a little bit of stuff that's not two atoms, but like they are so few that the heat capacitance ratio is pretty much 1.4. Okay, so now we know Cp is 1.4 times Cv, which means this process, which is follows Cv, right? This is a constant volume, is going to be less. 1 second. Yeah, adding. So adding. Okay, so when Cp is larger, tell me which process actually get me a higher temperature. Yeah, so Cp is higher, right? So the heat capacitance under constant pressure is higher. Does that mean at constant pressure, adding the same heat get me a higher or lower temperature? Higher capacitance means what? What is heat capacitance? Yes? It'll be a lower temperature, exactly, because higher capacitance means the same amount of temperature can contain more heat. Okay, so by raising this at a higher temperature, like a higher heat capacitance thing, think of water, right? Has a lot of heat capacitance. You need to add a lot of heat for the temperature to raise by a little bit. So, which means Cp is higher, meaning that at the constant pressure, by adding the same heat, you get only a smaller temperature increase. So, in the right, which means remember, like we are the constant temperature lines are 45 degrees, right? So if 45 degrees are the constant temperature lines, would the green and the red get to the same constant temperature line or not? They are not, right? And which one is going to get to a higher constant temperature line? The red one, exactly. So let's modify it a little bit. The red one needs to go like here. And now, what is the difference? What is the ratio? Okay, so the gap between the different purple lines are how much temperature increase there is. And we know the ratio of heat capacitance is gamma. So the ratio between the gap here and the gap here has to be gamma, right? Okay, so if the gap here is 1, then the gap here is going to be 0.4, because the total gap between the original state and the end of the red has to be 1.4 times the gap between the original state and the end of green. Now somebody tell me what is the slope of this blue line? Yes, the slope is shallower than gamma, right? It has to be shallower than 1. It has to be 1 over gamma. So, okay, so the slope is 1 over gamma. That's for isentropic expansion. We derived it, right? We didn't just tell you for isentropic expansion how much would the change in volume depend on the change in pressure. So that's just a derivation from the definition of the heat capacitance ratio. If you have a different heat capacitance ratio, the slope is going to be different. Okay, so how does the slope tell you the remember, the slope is a slope in the log-log plot, right? Okay, how does it tell you about the fractional sensitivity? What is the fractional sensitivity of pressure to volume during isentropic expansion? Which is, how does delta P over P is equal to what times delta V over V? Delta P over P is this part, right? In log-log plot, it's how much there is on here. And the delta V over V is how much decrease is in here. What is the ratio of this versus this? It's gamma. Actually minus gamma, right? Because this goes, delta P over P is positive, delta V over V is negative. Okay, so this thing is going to be minus gamma. We derived it. Okay, so how about the pressure to density? What is how can we change the delta over V? Delta V over V to delta rho over rho. Remember, this is for fixed mass of air, right? Yeah, I just multiply another minus 1. So delta V over V is exactly minus delta rho over rho. So gamma times delta rho over rho. Alright? Basically, we have derived that the heat capacitance ratio is not just a ratio of heat capacitance, but like a ratio of the fractional change of pressure over the fractional change of density. Okay, so we are going to see how that is useful. I mean, that's probably one of the most useful relations of ideal gas when you are deriving aerodynamic impact, right, of compressibility, right? So basically, when you have compressibility, the density is going to change. Density change leads to a pressure change. Pressure change now drives aerodynamics, right? Or you can think about the other way. When the pressure changes due to aerodynamics, the density is going to change. And density changes actually impacts the conservation of mass. Because if you have denser air, you only need a smaller volume to get more stuff through, right? When density decreases, you need a bigger area to get the same amount of stuff through. So let's see how that affects aerodynamics. Okay, any questions on this? I mean, this is the only thing we're going to use on the next slide. But you should be able to derive something like this by yourself. If not, you can ask me after class, or just try to derive it yourself. If you cannot, ask me. All right? Okay. Now we are considering air accelerating isentropically along the x-axis. Just to think about the wind tunnel we toured a few like a month ago, right? We have this before the test section. There is this huge contraction, right? The ratio was 8:1 in terms of the area. So just to think about the air accelerates from the upstream of the test section into the test section. And let's consider just the same Navier-Stokes equation we have been talking about before. And again, let's ignore viscous effects. Viscous effects actually happens near the wall, but in the middle, there is not much viscous effect. So du dt is the acceleration. For steady flow, dt can be written as dx divided by u, right? So du dt is basically u times du dx, because dx is equal to u times dt, right? Okay, and that is equal to this is minus dp dx is the force per volume, and the rho is the mass per volume. So this is basically force over mass, right? So it's equal to acceleration. So this is what it is. And let's actually use this to derive something very interesting. That is, how does the geometry of a flow is impacted by compressibility. So over a small segment of the streamline, pressure has changed by, of course, this much, right? dp dx times the small delta x. What is the resulting change in density? Somebody use what we learned previously. What is dp over p? How does this relate to change in density? Is equal to delta rho over rho. Is there any multiplier or anything? Yes? Gamma, yeah, 1.4 times delta rho over rho. Alright? So now if delta p is equal to this, it's basically dp dx times delta x, right? Okay? So my delta rho, let me just write it down in red. My delta rho, therefore, is equal to there is over p. Sorry, I forgot the over p here. Over p still needs to be here. Okay, then delta rho here is going to be gamma rho, and again still divided by p. No, not by p. Times this delta p, right, which is basically delta dp dx times delta x. All right. Okay, and let me just write it down. Rho over p times dp dx times delta x. All right. Okay. So now we want to not just relate the density change to pressure change, but now also relate the velocity change to density change. So now we actually get into compressibility, right? Compressibility is how would the air gets compressed when in different regions of the flow field. Different regions of the flow field means the velocity different, right? So imagine as the air goes from the starting chamber to the test section, how much has density changed? That's the question we want to answer. I don't know what happens. Okay, yeah, it's live back again. So let's start to use this equation. In this equation, we know u times du dx is equal to minus 1 over rho times dp dx, right? So dp dx can be related to velocity by multiplying both sides by minus rho. So I get rid of the minus rho over here, I get minus rho over here. So now let's plug this dp dx into here. Okay, so my delta rho is now equal to gamma rho over, is that right? One second, I think I put the gamma in the wrong side, right? D rho, I need to divide by gamma, not multiply by gamma on this. Is that right? So this gamma has to be in the denominator. Sorry for that. Right, here I'm basically going from a delta rho, right? I need to divide both sides by gamma, so gamma should be underneath, right? Okay, so here, which means, so d rho is equal to this times dp dx, and dp dx is minus rho u du dx times delta x. Okay, so du dx times delta x is how much the velocity has changed over that small segment. So let me just write it as delta u. So I have minus rho squared gamma p times u times delta u, right? Okay, so here is the changing velocity, and I really would like to express the changing velocity in relative terms, in fractional sensitivity terms. So I want to see how does the fractional sensitivity, how does the percentage of changing density relates to the percentage change in velocity. So let's do that. We do that by dividing both sides by rho, so delta rho over rho, so that's the fractional change in density, right, is equal to minus, well, rho gets cancelled out for 1, so I still get a rho but no longer squared, u over gamma p. Then times du, but I want du over u, so I have to square the u here. Got it? So this guy here is the ratio, right, of the fractional, is the fractional sensitivity of density with respect to velocity. Actually, let me put the bracket here. Because we know this is negative. When the velocity increases, right, it's driven always by a favorable pressure gradient. The pressure has to decrease, right? That's kind of the first question I ask you in the wind tunnel. Is the pressure in the setting chamber higher or in the test section higher? Of course, the pressure is higher upstream, right? It's lower when it speeds up. So when the velocity increases, the pressure always decreases, and thereby the density always decreases. The fractional sensitivity is always negative. But exactly how negative it is controlled by this thing. Okay? So for those of you who might still remember something from Unified, does this recall anything? It doesn't recall anything. So let me write it a little bit more. So this thing, rho u squared over gamma p, can be written as the square of u over the square root of gamma p over rho, right? Now, does this recall anything? It's square of the Mach number. This square root thing is speed of sound, right? Okay, so here I didn't derive speed of sound. I mean, there is no sound at all in this thing, right? But we just derived it directly, this square of the Mach number. Actually, Mach number by itself is not really that significant in aerodynamics. It's the square of the Mach number that appears everywhere. Okay, so let's just remember this thing being very important. This is the fractional sensitivity of density to velocity. This is compressibility, right? Okay, if my velocity increases by 1%, how much does the density drop? Well, if I'm at Mach 1, I'm going to answer to you, the density drops exactly by 1%. Okay, if I'm Mach 0.5, velocity increases by 1%, how much does density drop? At Mach 0.5. Well, again, this thing is the fractional sensitivity, right? And it's this. It's velocity divided by speed of sound squared, right? Mach squared. Again, at Mach 0.5, if velocity increases by 1%, how much does density drop? 0.25%. Okay, so it's Mach squared. At Mach 2, if my velocity changes, if velocity dropped by 1%, how much would density increase? 4%, exactly. So it's Mach squared that actually matters over here. Okay, so this is actually not the most significant result. the most significant result is the following. What is the fractional sensitivity of mass per area? Right? What is mass per area? It's the mass flux per area is rho times u, right? Okay, so what is the delta rho u divided by rho u itself? Again, it's the first thing we learned about fractional sensitivity. The fractional sensitivity of a product is equal to what? The sum of the fractional sensitivity, exactly, delta rho over rho plus delta u over u, right? Now we already expressed the delta rho over rho as a function of delta u over u, right? And let me just write it down, minus m squared times delta u over u. Now what is that? Somebody tell me, this is equal to what times delta u over u? One minus m squared, right? Because 1 corresponds to this existing delta u over u, and this is minus m squared. Okay, now this is more significant. Why? Because there is a sign change as you reach Mach 1. There is a sign change. Okay, in subsonic flows, if I speed up, how does my mass per unit area change? If the velocity increases, right, the mass per unit area increases, right? The extreme case is in incompressible flow when density is constant, right? I mean, this is actually why we consider low Mach flow as incompressible flow, because for low Mach flow, the relationship between the mass per area and velocity is the same as exactly incompressible flow, right? Okay, so if I speed up, if rho is constant, of course my rho u increases, right? Proportionally. But at finite Mach number, that's no longer true, right? And as Mach increases, the increasing uniform mass flow per area actually is not as much as the increasing velocity anymore. And exactly at Mach equal to 1, if I speed up, I get nothing. Okay, I get nothing out of a speed up. And at supersonic speed, it's opposite. If I increase in velocity, I get less flow per area. Okay, that's the most counterintuitive thing about supersonic flow that you are going to encounter. Okay, so this is just a corollary. What is the fractional sensitivity of stream tube area? So for stream tube, rho u a is the stream tube area, is equal to constant, right? And again, you learned about the fractional sensitivity of a product. So, well, if this is constant, the sensitivity as you go downstream or upstream is going to be 0, right? And the product fractional sensitivity is, of course, this plus this, right? All right? Which means delta A over A is exactly equal to minus of delta rho U over rho U. Okay, so how does this change as you speed up? I mean, this basically tells you, does my stream tube shrink or expand, right, as I accelerate? At subsonic speed, let me just write it back. This is m squared minus 1, right, the delta U over U. So at subsonic speed, when I speed up, my stream tube area decreases. And at Mach 0, it's proportional. If I speed up by 1%, my stream tube area decreases by 1%. At Mach 1, if I speed up, this stays constant. So it's almost like the flow becomes rigid. If I speed up, the flow tube area doesn't change. And now, when I becomes supersonic, this guy becomes positive. So if I accelerate, the flow expands. Right? This is the fundamental reason. Like if you design a wind tunnel for supersonic flows, the wind tunnel looks like that. Right? I mean, this is the supersonic flow. This is Mach 1, and this is subsonic flow. This is also why, like a rocket nozzle looks like this. Right? Subsonic flow, supersonic flow. All right. So in next lecture, let's actually expand this and put this relation into a real aerodynamic scenarios and explain how compressibility is going to affect aerodynamics. Okay, so see you.
just from taking the log and then differentiating that.
Yes, just take the log and differentiate that. Exactly. Yeah, that's easiest way to derive it. Yeah. Yeah.